Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. My experimental discovery of 1989 of how and why parallel processing makes computers faster and makes supercomputers fastest was not in the supercomputer textbooks that were printed in the 1970s and 80s. That experimental discovery of parallel processing was a real game changer that ushered an explosion of research and the commercialization of the modern supercomputer that computes many things at once. In the 1980s, there was a big gap between the fastest supercomputer we had and the fastest supercomputer we needed. I started my quest for the parallel processing supercomputer with the question, can parallel processing be experimentally confirmed? I began my quest for the fastest supercomputer by stating my parallel processing hypothesis, namely that I could evenly divide each grand challenge problem of extreme scale computational physics and divide it into 65,536 less challenging problems. My central experiments that led to my discovery of parallel processing comprised of speedup measurements across a new internet that I visualized as my global network of 64 binary thousand processors. After my decade of trial and error in programming loosely coupled ensembles of processors, I experimentally discovered a speed increase of a factor of 64 binary thousand and discovered that speed up across as many processors. What made the news headlines in 1989 was that I experimentally discovered massively parallel processing and invented the technology when the supercomputer textbooks considered computing many things at once and doing so to solve extreme scale problems in physics and beyond to be both theoretically and physically impossible. I experimentally discovered that parallel processing is not a waste of time. I experimentally discovered that computing many things at once makes computers faster and makes supercomputers fastest, and I invented how to use that new supercomputer knowledge to build a new supercomputer. My experimental discovery of massively parallel processing led me to discard the sequential processing hypothesis that was erroneously formulated by Jean Amdahl back in April 1967 and that was the reigning supercomputing paradigm of the 1940s, 50s, and 60s. My experimental discovery of massively parallel processing led me to discard the vector processing hypothesis that was championed by Seymour Cray and that was the reigning supercomputing paradigm of the 1970s and 80s. My experimental discovery of parallel processing made the news headlines and was in the June 20, 1990 issue of the Wall Street Journal and was in the June 27, 1990 issue of the Chronicle of Higher Education. The core essence within those headline stories was the new supercomputer knowledge of how and why the supercomputer scientist must parallel process across processors that encircled a globe and encircled it in the manner computers on the internet encircled a globe. That experimental discovery is embodied in multifunctional computers and in all supercomputers. It should be noted that the supercomputers of the past were not used the way the supercomputers of the present are used today. After World War II and after 1946, programmable supercomputers were used to solve textbook problems such as ordinary differential equations from calculus textbooks. 7 decades later, the supercomputer that is powered by 10,649,600 commodity off-the-shelf processors is used to solve global problems such as general circulation models that are used to foresee otherwise unforeseeable climate changes. Back in 2006, China unveiled its plan to invest $112 billion in scientific research and to do so by 2020. One of the products from that ambitious quest was the world's fastest supercomputer that was made in China. That fastest supercomputer was powered by parallel processing across 10,649,600 commodity off-the-shelf processors. By 2020, China hopes that 60% of its economic growth will arise from its investment in high technology. The uncharted fields of knowledge is the new land to be explored and colonized. That new land is explored the way Mungo Park explored the River Niger of West Africa. The exploration of Mungo Park opened the door for Great Britain to colonize my country of birth, Nigeria. I am the Mungo Park of the supercomputer world that was searching for the fastest computation ever. I was searching for the new supercomputer that computes in parallel instead of in sequence. In the new land of parallel processing supercomputers, you are either a colonizer or the colonized. China intends to become a colonizer in the frontier of science. Africa is still contented with being colonized in the frontier of technology. This is the reason the United States has raised an alarm cry over the alarming resources that China is investing to become a colonizer in the frontier of the supercomputer. The answers to the toughest questions in extreme scale computational physics were not in the physics textbooks of the 1980s and earlier. I discovered the answers to those tough questions and discovered them across a new internet that is a global network of 64 binary thousand commodity off-the-shelf processors, or across a new internet that is a global network of as many identical computers. My supercomputer discoveries were not taught in the classrooms of the 2 decades of the 1970s and 80s. My experimental discovery of massively parallel processing opened the door to a revolution, namely computers and supercomputers that could solve many problems at once or in parallel. Back in the 1980s, both Gene Amdahl of Amdahl's law fame and Seymour Cray, who pioneered vector processing technology for supercomputers, were the strongest opponents of incorporating parallel processing technology into the modern supercomputer. Seymour Cray is best remembered for ridiculing and rejecting the massively parallel processing supercomputer and for mocking the technology in his famous quote. Seymour Cray joked that, quote, "If you were plowing a field, which would you rather use, 2 strong oxen or 1,024 chickens?" Unquote. In my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July of 1989, I used 65,536 chickens instead of 1 strong oxen. I was the strongest proponent of parallel processing. For that reason, I was the lone wolf programmer of the most massively parallel supercomputer ever built as of the 1980s. Seymour Cray designed more vector processing supercomputers than anyone else designed. As the most experienced supercomputer scientist that he was, the supercomputer industry listened to Seymour Cray, not to me, Philip Emeagwali. My experimental discovery of how to solve a million or a billion computation-intensive problems and how to solve them at once or in parallel made the news headlines because I proved that the computer powered by only 1 processor can do whatever the supercomputer powered by 10,649,600 commodity off-the-shelf processors can do if and only if the computer has 30,000 years to compute what the supercomputer computed in only 1 day. For that experimental discovery, it is often said that Gene Amdahl is to sequential processing supercomputers what Seymour Cray is to vector processing supercomputers, and what Philip Emeagwali is to parallel processing supercomputers. Please allow me to introduce myself. Who is Philip Emeagwali? I was the only full-time programmer of the most massively parallel processing supercomputer. I was the only full-time programmer of the most massively parallel processing supercomputer. Please allow me to introduce myself. Who is Philip Emeagwali? I was the only full-time programmer of the most massively parallel processing supercomputer of the 1980s. I visualized that massively parallel processing supercomputer as a small copy of the internet. I experimentally discovered that massively parallel supercomputer to be a new internet and a global network of 65,536 processors that I visualized as encircling a globe that I also visualized in a 16-dimensional universe. More importantly, the reason I was the only full-time massively parallel processing programmer of the 1980s was because I was the only supercomputer scientist that had the in-depth knowledge across the fields of the frontiers of mathematics, across the frontiers of physics, and across the frontiers of computer science. That interdisciplinary knowledge was needed to program that massively parallel processing supercomputer and needed to give research lectures to research mathematicians, research physicists, and research supercomputer scientists. I was the only supercomputer scientist that I know of that was trained for 16 years onward of June 20, 1974. I was the only and the first supercomputer scientist that gave full-breadth public lectures on massively parallel processing and gave those lectures in the early 1980s. In the early 1990s, I was appointed as the distinguished speaker from the Association for Computing Machinery to American University Computer Science Departments, and I lectured on parallel processing supercomputing. The Association for Computing Machinery is the premier society for computing professionals. In the early 1990s, I was also appointed as the distinguished visitor from the Computer Society of the Institute of Electrical and Electronics Engineers, or IEEE, to American University Computer Science departments. The Institute of Electrical and Electronics Engineers is the world's largest technical society. The videotapes of my lecture series on parallel processing are posted at emeagwali.com. I lectured on how I experimentally discovered how to program massively parallel processing supercomputers that were powered by 2 to the power 16 processors, and how to use my experimental discovery to solve the toughest problems in physics that were previously impossible to solve. I experimentally discovered that the massively parallel processing supercomputer can solve problems in extreme scale computational physics that the sequential processing computer cannot solve. I experimentally discovered that the massively parallel processing technology scales linearly from 1 processor to 1 billion processors and beyond 1 billion. I experimentally discovered that the massively parallel processing technology connects many processors into a unified supercomputer, whether it's 64 binary thousand processors or 64 binary billion processors. That scalable, massively parallel processing supercomputer of the 1980s that was invented as today's modern supercomputer will hopefully be reinvented for tomorrow's planetary supercomputer. My first entry into the unexplored territory of massively parallel processing supercomputing felt like a David versus Goliath battle. I, Philip Emeagwali, was the David and the proponent of massively parallel processing supercomputers. Seymour Cray and Gene Amdahl were the Goliaths and the proponents of scalar and vector processing supercomputers, respectively. The reason the likes of Seymour Cray and Gene Amdahl believed that it will be physically impossible for me to massively parallel process and do so across an ensemble of 64 binary thousand commodity off-the-shelf processors was because they were trained for only 6 years. Seymour Cray and Gene Amdahl were only trained on how to sequentially compute and compute with only one processor. The reason the pioneers of sequential processing supercomputing of the 1950s and 60s and those of vector processing supercomputing of the 1970s and 80s argued that parallel processing will forever remain a huge waste of everybody's time was because they lacked the 16 years of mathematical maturity that I acquired onward of March 25, 1974. My contributions to algebra, calculus, and computational mathematics was the cover story of top mathematics publications that are read by research mathematicians. Seymour Cray and Gene Amdahl needed to fully understand the parallel processing supercomputer technology and can only do so by first understanding the extreme scale computational science behind the fastest supercomputing. It's impossible for Seymour Cray or Gene Amdahl to understand the most advanced expressions in calculus, that is a subset of massively parallel processing, without foremost having a decade and a half of specialized training on how to solve initial boundary value problems that are governed by a system of coupled nonlinear and time-dependent partial differential equations of modern calculus called Emeagwali's equations. In an abstract lecture on advanced calculus and extreme scale algebra that I delivered on July 8, 1991 in Washington, District of Columbia, United States, I told mathematicians attending the International Congress of Industrial and Applied Mathematics the following. As a research mathematician and as a research physicist, I always knew the fact that the scientific discoverer discovered a truth, whereas the inventor of a partial differential equation formulated possibilities. A computer scientist that only trained with computers, that only computed with one processor, will not understand the partial differential equations and therefore will not understand how to massively parallel process and how to do so across a new internet that is a global network of 64 binary thousand commodity off-the-shelf processors. So my combined knowledge of physics, calculus, algebra, and massively parallel processing was greater than the combined knowledge of Seymour Cray and Gene Amdahl that were only trained with computers that computed with only one processor that was not a member of an ensemble of processors. That gap in scientific knowledge is evident by watching and doing a side-by-side, videotape by videotape comparisons of the scientific lectures of Seymour Cray, Gene Amdahl, and myself, Philip Emeagwali. There was no shortcut that could have enabled Seymour Cray or Gene Amdahl to understand in 6 years what took me 16 years to understand. It's as physically impossible as a 6-year-old fighting a 16-year-old Muhammad Ali for the future world heavyweight boxing championship. 2,300 years ago, a young prince asked Euclid, the father of geometry, for a shortcut to geometry. Euclid said to the young prince, quote, "There is no royal road to geometry," unquote. I was the first supercomputer scientist that articulated how he experimentally discovered massively parallel processing and discovered it as the technology that makes computers faster and makes supercomputers fastest, and invented how and why to use that new supercomputer knowledge to build a new supercomputer that encircled a globe and encircled it in the manner the internet encircled a globe. In the 1980s, I articulated how I named each of my 65,536 processors, and I articulated how I commanded each processor to send and receive emails and do so to and from the other 65,535 processors. This technical aspect of my contribution to the experimental discovery of parallel processing was lost to the lay public in part because it involved abstract and dense mathematical knowledge of calculus, algebra, topology, and graph theory. My system of coupled nonlinear and time-dependent partial differential equations of modern mathematics, called Emeagwali's equations, were developed only for research computational mathematicians. It's impossible for the layperson to understand partial differential equations. How to accurately solve partial differential equations could only be understood by a few dozen people that were actually experimenting with massively parallel processing supercomputers. Over the years, I learned that conversations about parallel processing is a party spoiler, even amongst supercomputer scientists that only believe in vector processing supercomputing. I began programming sequential processing supercomputers on Thursday, June 20, 1974, at age 19 at 1800 Southwest Campus Way, Corvallis, Oregon, United States. That sequential processing supercomputer was the world's fastest in the mid-1960s. By definition, a sequential processing supercomputer is powered by only one powerful processor. Therefore, it was not necessary for me to name that sole processor. My unique naming of my 65,536 commodity off-the-shelf processors was the abstract elephant in the supercomputer center. Those 65,536 unique names were the as many uninvited guests to the unexplored territory of the massively parallel processing supercomputer. That lack of understanding of how to uniquely name those processors added weight to the saying that parallel processing is a huge waste of everybody's time. The June 14th, 1976 issue of Computer World, the flagship publication of the world of computing, described parallel processing as a quote-unquote waste of time.
Insightful and brilliant lecture.